Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 3, Section 1, Chapter 3, Topic 3. Unraveling Convection in Semiconductor Packaging. Understanding Newton's Law of Cooling, Velocity and Thermal Boundary Layers, and the Heat Flow Equation. Introduction. In the intricate landscape of semiconductor packaging, the efficient dissipation of heat is essential for maintaining the reliability and performance of electronic devices. Convection, one of the primary modes of heat transfer, plays a crucial role in semiconductor packaging by facilitating the removal of heat from the package to the surrounding environment. This overview delves into the elements related to convection in semiconductor packaging, exploring Newton's law of cooling, velocity and thermal boundary layers, and the heat flow equation. Fundamentals of convection. Convection is the process of heat transfer between a surface and a fluid medium, liquid or gas, through the combined mechanisms of advection and diffusion. Advection refers to the bulk movement of fluid, carrying heat away from the surface, while diffusion involves the molecular transport of heat within the fluid. Convection is characterized by fluid motion driven by temperature gradients, with warmer fluid rising and cooler fluid sinking, creating convective currents that facilitate heat transfer. Newton's law of cooling. Newton's law of cooling describes the rate of heat transfer between a solid surface and a fluid medium due to convection. According to Newton's law, the rate of heat transfer, Q, is directly proportional to the temperature difference, delta T, between the surface and the surrounding fluid, expressed as Q equals H dot operator A dot operator delta T, where Q is the rate of heat transfer, W. H is the convective heat transfer coefficient, W per square meter K. A is the surface area of heat transfer, M squared. Delta T is the temperature difference between the surface and the fluid, K. The convective heat transfer coefficient, HH, accounts for the effectiveness of heat transfer between the surface and the fluid, influenced by factors such as fluid velocity, fluid properties, and surface geometry. Velocity and thermal boundary layers. In convection, the velocity and thermal boundary layers play a crucial role in shaping the heat transfer process near the surface and within the fluid medium. The velocity boundary layer refers to the region near the surface where fluid velocity changes from zero at the surface to the free stream velocity of the fluid. Similarly, the thermal boundary layer is the region near the surface where the temperature gradient changes from the surface temperature to the bulk fluid temperature. The thickness of the boundary layers depends on factors such as fluid velocity, fluid properties, and surface roughness. In semiconductor packaging, optimizing boundary layer thicknesses is essential for maximizing heat transfer rates and minimizing thermal resistance. Heat flow equation. The rate of heat transfer due to convection can be quantified using the heat flow equation, which accounts for both conduction and convection mechanisms. The heat flow equation is expressed as Q equals minus K dt, dx plus H dot operator A dot operator delta T, where Q is the rate of heat transfer, W. K is the thermal conductivity of the material, W per meter K. dt, dx is the temperature gradient, K per meter. H is the convective heat transfer coefficient, W per square meter K. A is the surface area of heat transfer, M squared. Delta T is the temperature difference between the surface and the fluid, K. The first term on the right-hand side of the equation represents heat transfer by conduction, while the second term represents heat transfer by convection. The relative contributions of conduction and convection depend on factors such as material properties, surface geometry, and fluid flow conditions. Thanks for watching. Please like, share, and subscribe.